Hey guys, so in these few set of videos we are trying to understand the art of the state creation, that is dynamic programming. And in this particular video we will see how to solve a very standard dynamic programming problem, that is the longest increasing subsequence problem, using memoization. In the previous video we already saw how to solve this exact same problem using tabulation. So for those who don't really know the problem, in the problem you are given an array ARR with of a particular length n, and you have to find the length of the longest increasing subsequence for this array. For example, let's take this example over here where the array is 615. In this case, the increasing subsequences will be 6, 1, 5 and 1 comma 5. And among all of these, the longest one is 1 comma 5, so the length of the LIS becomes 2. So that's our answer. And the second case, the array is 4, 3, 2 comma 1. In this case, the increasing subsequences are 4, 3, 2 and 1 respectively. Since all of them are of length 1, the answer becomes 1. All right, so let's see how we can actually memorize this entire thing up. So first let's just have a function lis that takes in an integer array as an input, and it also computes the value of the answer that we are looking for over here. So the first thing, whenever we solve a dynamic programming problem, we had discussed in one of the tutorials that we divide that problem in 3 different sub problems. All right, so let's just get into that first. The first sub problem was defining the states of the DP. So in this case I'm going to define DP of I as nothing but the length of the longest increasing subsequence starting from index I. The length of the length of the LIS starting from index I. All right, now the second thing is laying down the recurrence relation. So in this case, dp of I is equals to 1 plus max of dp of j for all j such that j is greater than I and j is less than n, and the third criteria is arrj should be greater than arri. So this is our recurrence relation, and this is also the second sub problem. And the third sub problem was laying down the correct topological order in which we have to solve the states. So as we have already discussed, in the case of memoization, the third sub problem is irrelevant, all right, because we use a wrapper function over here, and that wrapper function ensures that you don't really need to follow a correct topological order to solve the states in. Even though you can, it's basically a top down approach, all right. You can call the wrapper function with any of the states, all right, and that wrapper function will call the children states or the states that the current state is depending upon implicitly, all right. So because of that, in this case you do not really need to actually lay down the correct topological order to solve the states in, because the wrapper function takes care of that. So now that we have defined, so let's just completely ignore the third sub problem. In this case we don't really need that over here because we are memoizing. Now let's just create a wrapper function over here. Okay, so the wrapper function, what it will do is, let's just call it lis wrapper. So in this function you will need to pass in a particular state of dp, and it will compute the value of that state for you, and it will return the value of that state. It will compute it and return it. In case it's already computed, it will directly return it, all right. So the other thing that it will take is vector int and arr. All right, so I've just defined this function for now, but we will get into the coding part of this function after a while. All right, so first things first, I'm going to define a global I'm going to define 2 global arrays over here. All right, so it's not really necessary to make these 2 arrays global, but it's convenient, all right. It saves some time. So for those who don't really want to make this array global, these 2 arrays global, you can actually choose to pass them as reference in the wrapper function, but for this case I'm just going to make them global. So let's call the first array as vector in dp and the second array as vector bool v. All right, so these 2 variables will actually be accessed inside this wrapper function over here. That's why we have made them global. And let's just understand the significance of these 2 arrays first. So dp array is just very straightforward. dp of I will store the value of ith state of dp, that is the length of the longest increasing subsequence starting from index I. The visited array is also like, it's like a an array. It's like an array to support the LIS wrapper. It tells whether a particular state has been solved or not. All right. So if VIS of I is true, it means that that particular state has been solved and it has been cached inside memory. So we do not really need to solve this particular state again. All right. So this is the significance of the visited array over here. So let's just now complete the wrapper function now, and then we will get into the main function after that. All right. So how do we actually code this wrapper function? So whenever we are coding a wrapper function up, I follow these steps. First, I lay down the base cases. So in this case, for the longest increasing subsequence problem, there is no as such a base case for this definition of for this particular definition of DP. There is not any base case as such, so we can ignore this for now. The second part which I focus upon is checking whether a particular state has been visited, or that is checking if a particular state has been solved or not. If the particular state has been solved, I am directly going to return its value from the cache. All right, and the cache over here is nothing but this global array vector in DP. All right, so check if a state has been solved. All right, so to do that, all I need to do is if VIS of I, in that case I can return the value of DP of I. Otherwise I need to compute the value of DP, that is compute the value of DP of I. So to do that, it's very straightforward. First I will initialize DP of I as 1. And why is that? Because the minimum length of the longest increasing subsequence has to be at least 1. All right, the minimum length of DP of I has to be at least 1. That is the ith element itself. All right, so how do I proceed with this next? All right, so to do that, all I will do is for all j's between I to n, that is for int j equals to I plus 1, j less than n, j plus plus. So you can replace this n with arr.size over here, because this we don't really have a variable n over here. You can choose to define a variable n over here if you want to for your convenience, but in this case I'm just going to iterate between I plus 1 to arr.size, because this arr.size is nothing but n itself. All right, so that is the size of the array. Now what I will do is I will check if and only if arrj is greater than arri, I am going to update dp of I as dp of I equals to max of dp of I comma 1 plus. Now what you need to do is you need to call this LIS wrapper with jth element comma arr. Now for those who are having it out, why can't I actually pass why can't I just use dp of j over here instead of this LIS wrapper? All right, why do I need to make this recursive? Because the simple answer is you have not really computed the value of dp of j over here. All right, so if you are not if you have not actually ensured that you have computed dp of j before, you cannot that's why you have to use this LIS wrapper over here, because if a particular state has not been solved, it computes it and then it returns its value. All right, that's why we always use LIS wrapper, and that's why this entire memoization approach is also known as top down approach. All right, because whenever a particular state is called for the first time, it has never been solved before. So that's why that's another reason I have to use the LIS wrapper over here. So I hope you guys got a feel for why we are using the LIS wrapper over here. Now that we have computed all of this, all we need to do is we need to mark this particular state as solved. All right, so mark the state as solved. So in that case, all I need to do is mark visited of I as equals to 1. All right, so that's all with like the computation part, and now all we need to do is return the value of dp of I. So that completes our what you can say is that completes our the wrapper function over here. All right, so now that we have completed our wrapper function up, let's see how we can code this LIS function over here. How am I going to use this over here? Now if you notice, the final answer in this case, the answer that we are looking for is nothing but max of dp of I for for all I greater than, let's say, 0 and greater than equals to 0 and I less than n, and that's all right. So basically this is what we are looking for. All right, we have to find the maximum of all the dp of I for I greater than equals to 0 and I less than n. Why? Because dp of I represents the length of the longest increasing subsequence starting from index I. All right, so we have to find the length of the longest increasing subsequence from any of these indices that can start from any of the index I in the array. So I have to take the maximum of all of these. So that's how we are going to compute the answer over here. So now that we have these three over here, let's just keep them over here. Now what I will do is I am going to initialize these two global variables over here. So to do that, I'm going to resize dp with arr.size, and I'm going to resize the visited array always as well at vis.resize arr.size comma 0. That means it has all of it, it has not been solved before. All right, that's why I'm resizing it with 0. All right, now all I need to do is I need to iterate over all the values from I equals to 0 to I less than arr.size. arr.size is nothing but n, and do I plus plus, and then I need to update my answer as answer equals to max of answer comma if you notice, I need to call lis wrapper over here I comma arr. All right, and then you can return the value of answer as return answer. So basically this is how you code up this function over here, this lis function over here. Now we have coded up the lis wrapper and the lis function, and the next thing that we need to do is I need to have a driver function over here. So let's just say that the driver function takes in an integer n as an input, and it also takes in an integer array as an input. So let's just call it vector int arr n, and I'm going to iterate from int I equals to 0 I less than n I plus plus, and then what I will do is scene arri over here. Then what you have to do is you have to see out lis arr. So that's all for the coding part, and let's just check if this code is working or not. All right, so let's just get into that over here. All right, so for the first test case, if you notice, the test case was 5 1 2 3 4 5, and for this particular test case we got the correct answer, that is equals to 5. The second test case was 4 4 3 2 1, that is the array over here is 4 3 2 1, and the length of the lis is 1 in this case, and that is the correct answer. The third test case is 6 1 4 2 3 4 5. So in this case the array is 1 4 2 3 4 5, and the answer is 5, that is correct. The answer is 1 2 3 4 5 in this case. All right, and the last test case is 1 comma 10, and answer for this one is equals to 1. So this is how we actually code up a memoization problem. I hope that you guys got a gist of it, and it's okay if you didn't really get it completely. All right, with practice you will get better at it. All right, so all you guys need to do is just practice and practice a lot of questions on dynamic programming, and in the coming videos we are going to solve a lot more problems. All right, so there will be a lot of problems and a lot of interesting problems to solve on dp. So but before that we also need to do one more thing over here. All right, I completely forgot about that. We have to talk about the time complexity. So time complexity of this problem over here is O of n square. And why is that? Because if you notice, whenever I want to compute the value of whenever I want to compute the time complexity of a dynamic programming problem, I look at two things: the number of states, that is the first thing, and the time to compute each state. All right, so in this problem over here, the number of states are n, and the time to compute each state is also O of n. Why? Because just look at this part of the code over here. All right, this is the time actually required to compute a particular state, and this is so the time to compute each state is actually O of n. All right, so basically on an average you take O of n time to solve a state, so the entire runtime becomes O of n square in this case. The second part is the space complexity, and the space complexity for this problem is also O of n in this case. So to understand these two things better, I would recommend that you guys lay down you guys try to understand the entire recursion tree for this LIS wrapper over here, how it's going to work, how it's going to proceed, and then you will have a very beautiful understanding of the time complexity and the space complexity on your own. So basically that's all for this video, guys. I hope you guys got to learn a lot, and thank you for watching this.